In section 5.1, your author introduces us to the idea of the average value of a function. In this section, now that we understand what the definite integral is, we can actually define the average value of an integrable function. But I thought we'd start with that derivation first. So let's say someone gave us a function y equals f of x, and we know it's integrable. I've drawn a continuous function, but there are other kinds of integrable functions, right? There could be finitely many jump discontinuities and maybe something even weirder happening, but for right now, this will be our function. And let's just say someone asked us to find the average value of that function and say we knew nothing else. Well, we know what an average is, right? To find the average of something, you add a bunch of stuff up and then divide by the total number of things. So maybe we have the idea to take a few y values, just a few sample y values, and add them together. Like maybe that's a y value that corresponds to some C1 and some C2, C3, all the way to some C sub n. Right? We add all those y values together, and then we divide by the total number of y values. And we get something like that, and that should approximate the average value of the function. And assuredly, if I used more and more y values, it would get better. And then I start to understand that that is really the same as, well, this calculation, because dividing by n is the same as multiplying by 1 over n. And then I could write that down like this. And this is starting to look like a Riemann sum. Right now, it's not itself a Riemann sum because that's not a delta x, right? So if I could work on this just a little bit, right, then this is still approximating the average value, and then I could imagine taking a limit as n approaches infinity. So we assumed my function was integrable. So if I was to involve the definite integral, I could choose any partition I wanted to, and I could let the rectangles all have the same width, and I could even use right-handed endpoints if I wanted to, but right now all I want is for my rectangles to have the same width, b minus a all over n. And if I imagine dividing both sides of that equation by the quantity b minus a, I would see that 1 over n is equal to delta x over b minus a. That lets me come over here to this calculation and replace that 1 over n with a delta x over b minus a. Well, if I continue to look at that sum, excuse me, I have some old problems on those boards, but if I continue to look at that particular sum, the quantity b minus a is a constant, and I can pull a constant out from a sum. So my average value would be approximated by this sum times 1 over b minus a. Well, that's a Riemann sum, which would allow me to conclude that the average value of f should be equal to the limit, as n approaches infinity, of 1 over b minus a times that sum. And even better than that, 1 over b minus a is still a constant. I can pull that out front of a limit. And what I have here is the definition of the definite integral from a to b of f of x dx. The average value of an integrable function over the interval ab is 1 over b minus a times the definite integral from a to b of f of x dx.